frequency is to be measured. The operation of frequency meter can be understood from the phasor diagram shown below. When the magnetizing coil is connected across the supply, then current I flows through the magnetizing coil and sets off flux phi. If we neglect the resistance of the coil and the iron loss in the core, flux phi is in phase with the current I. Since flux phi is an alternating flux, it will induce EMF in the moving coil. So when the magnetizing coil is connected across the supply, the current I flows through the magnetizing coil and sets off flux phi. So flux phi will in phase with the current I. If we neglect the resistance of the coil and the iron close to the coil, the flux phi will be in phase with the current I. Since flux phi is an alternating flux, it will induce EMF in the moving coil. Uh, Flux phi is alternating and it will induce EMF, and this induced EMF will lags behind the current, or you can say that current leads the voltage by 90 degree. Uh, this EMF induced circulate a current in the moving coil. The current in the moving coil will be lagging or leading depends upon the circuit of the moving coils. If the circuit is inductive, the current will lagging, and if circuit is capacitive, current will be leading. When inductive and capacitive reactance are equal, the current I will be in phase with the EMF. Uh, so if current is lagging, so if circuit is inductive, the current I will lag behind the EMF by some angle, and if circuit is capacitive, the current will leads the EMF, and if circuit is resistive, or if capacitive reactance Xc and inductive reactance XL are equal, then the current will be in phase with the EMF E, or you can say that the circuit will behave as a resistive circuit. The deflecting torque acting on the moving system will be proportional to I small I cos 90 plus minus theta, where I is the current in the field or magnetizing coil, and small I is the current in the moving coil, and phi is the angle between current and EMF. Figure A shows a phasor diagram in which moving coil is assumed to be inductive. Therefore, current I lags behind the voltage by angle phi. The torque acting on a moving system, that is deflecting torque Td, is directly proportional to cos 90 plus minus theta. The figure B shows the phasor diagram in which moving coil is assumed to be largely capacitive. Therefore, current I leads the voltage by an angle alpha. Deflecting torque Td is directly proportional to uh, uh, current through a moving coil, that is small I cos 90 minus theta. Figure C shows the phasor diagram when the inductive reactance XL is assumed to be equal to capacitive reactance XC. Under this condition, the moving coil circuit is purely resistive, so the current I will be in phase with the EMF E. Therefore, deflecting torque Td is directly proportional to I cos 90. Cos 90 equals to 0, and deflecting torque will be 0. The capacitive reactance of the moving coil, that is Xc, is constant for a given frequency f, whereas inductive reactance XL of the moving coil is not constant. because its values varies with the position of moving coil on the iron core. The inductance of the moving coil circuit decreases as the moving coil goes away from the magnetizing coil. Now, coming to actual operation of the instrument, if the frequency is more than the inductive reactance XL will be more than the capacitive reactance XC, then torque will act on the moving system. So, under the influence of this torque, the moving coil will not move until XL is equals to XC. When XL and XC are equal, no torque act on the moving system, therefore it will not move further. The position of indicator will indicate the frequency at this position. The value of capacitor C is so selected that moving coil takes a convenient position on the iron core. If the supply frequency increase, the capacitive reactance decrease, because the formula of Xc is 1 upon 2 pi Fc. So if the supply frequency increase, the capacitive reactance Xc will decrease. Therefore, the moving coil then moves away from the magnetizing coil till its inductive reactance becomes equals to the capacitive reactance of the circuit. If the supply frequency falls, the capacitive reactance becomes more than the inductive reactance of the circuit. Then the moving coil moves toward the magnetizing coil till its inductive reactance becomes equals to capacitive reactance of the circuit. Next is power factor meter. The instrument used for the measurement of power factor is known as power factor meter. Power factor may be defined as the cosine of angle between voltage and current. The ratio and also power factor may be defined as ratio of true power, that is VI cos phi, and apparent power, that is VI. So ratio of true power and apparent power is also known as power factor. Figure shows the arrangement for finding the power factor of the load. The true power is measured by a wattmeter and the apparent power is calculated by the product of voltage and current. Therefore, power factor of single phase circuit can be calculated by noting down the reading of wattmeter, voltmeter and ammeter respectively. Power factor meter have two circuits, namely current circuit and pressure circuit. The current circuit carries the load current or fraction of the load current whose power factor is to be determined, and pressure circuit is split up into two parallel circuits. One circuit is non-inductive and the other is inductive. The deflection of the instrument depends upon the phase difference of the load current and the current in the two branches of the pressure circuit, that is upon the power factor of the load. Single phase dynamometer types power factor meters. It consists of two circuits, current circuit CC and pressure circuit P1 and P2. Current circuit consists of two fixed coils CC connected in series with the load and carries the load current. The pressure circuit also consists of two identical coils P1 and P2 of fine wire pivoted at the same spindle, and both are fixed at 90 degrees to each other. The pressure circuit coil P1 is connected across the supply end through a non-inductive resistance R, and pressure circuit coil P2 is connected across the supply terminal through the inductance L. The value of resistance and inductance are so selected that for the normal frequency the current in both the pressure coil P1 and P2 are same. Since the current in both the pressure coil is the same, therefore they will produce equally strong magnetic field which are 90-degree displaced from each other. If the phase displacement is not exactly 90 degree, it can be compensated by making mechanical angle between the two axes of coil P1 and P2 equal to electrical angle of difference between the two current. The pressure coil P1 and P2 forms the moving system and they move together. A pointer is also attached with the moving system which indicates the power factor of the circuit directly. The instrument has no controlling torque, therefore the pointer remains in its deflected position. Now the working of dynamometer types power factor meter. When the instrument is connected in the load circuit, current flows through the current coil CC and pressure coil P1 and P2. The magnetic field is set up by all these four coils due to the interaction of the fluxes. The turning moment or torque is produced. The moving coil starts moving and turns to such a position that the resultant torque experienced by the coil is zero. At the unity power factor, when the instrument is connected in the load circuit having unity power factor, the current in the pressure coil P1 will be in phase with the load current or current coil CC, and the current in the pressure coil P2 will lag by 90 degree behind the voltage or behind the current in the current coil CC. The coil P1 therefore will experience a turning moment and will adjust itself at a perpendicular to the axis of current coil CC, and the pointer will indicate unity power factor. At lagging power factor, when the instrument is connected in the load circuit having lagging power factor, in this case both the pressure coil P1 and P2 would experience turning moment in an opposite direction, and therefore the moving system will adjust itself at a position in between 0 and 1 depending upon the value. In the leading power factor, when the instrument connected in the load circuit having leading power factor, in this case the polarity of field in a current coil is reversed of that of considered above. Hence the moving system takes up an intermediate position on the leading side in between 0 and 1. Next is phase sequence indicator. This instrument are used to determine the phase of three-phase supply. The phase sequence means the order in which the phase of three-phase supply attain their maximum value of EMF. If the three-phase supply has phase sequence as R by B, it means that red phase will attain their maximum value of EMF. Uh, uh, Two types of phase sequence indicators are used. First is rotating type and second one is static type. In rotating types, it consists of three coils connected in star displaced at 120 degree apart. The three ends of the star connected coils are brought out and connected to three terminals marked as R, Y, B as shown in figure. Three-phase supply whose phase sequence is to be determined is connected to three coil of phase sequence indicator. An aluminum disc is mounted on a spindle. The disc acts as a rotor and is free to rotate. When the three-phase supply is given to the star-connected coil, a rotating field is set up which induce eddy current in the disc. A torque acts on the disc due to the motor action. The disc start rotating. The direction of rotation depends upon the phase sequence of the supply. Uh, if the phase sequence is correct, then the disk will rotate in a clockwise direction. If the phase sequence is incorrect, then the disk will rotate in the anti-clockwise direction. So from the direction of the disk uh, we can it can indicate that the direction of phase sequence is correct or incorrect. Next is instrument transformer. Two types of instrument transformer are used, that is current transformer and potential transformer. Current transformer are used to measure the current, and potential transformer are used to measure the voltage. Current transformer is a step up transformer. It step up the voltage and step down the current. And potential transformer is a step down transformer. It step down the voltage to the level of measuring instrument. Next is tongue tester. In this type of current transformer can use for with a single conductor. The core of CT can be split with the help of trigger switch, and therefore the core can be clamped around a live conductor to measure the current. This arrangement avoids the breaking the circuit for connecting CT. The single conductor acts as a primary, and the secondary is wound on the core of the CT. Ammeter is connected in the secondary, which gives directly the reading of the current flowing in the conductor, in which the value of current is to be measured.